Hello everyone. The title of our project is Constant Speed Control of DC Motor using PWM and Speed Monitoring using Digital Tachometer. The project members are Will 72, 85, 88, and 89. Pulse speed modulation or pulse duration modulation is a method of reducing the average power delivered by an electrical signal by effectively chopping it up into discrete parts. The average value of voltage fed to the load is controlled by turning the switch between supply and load on and off at a fast rate. We have used BLDC motor in our project. A notable disadvantage associated with BLDC motor is the generated back EMF by its winding when operated. Motors act as a generator when they are rotating. This means that a back EMF voltage is induced in the stator, which opposes the driving voltage of the motor. Back EMF is an important characteristic of a motor, as by looking at its shape, we can tell what kind of motor we have, and it also dictates the type of control algorithm we need to use to control the motor. BLDCs have a trapezoidal shaped back EMF. We have observed the back EMF shape in simulation. This is the block diagram of our project. Here we can see the Hall effect sensor, BLDC motor, three-phase inverter, commutation logic, PID controller. Here we will see desired output in data inspector mode.
Assalamu alaikum. I am Istiak Hassan Arnab, ID 89. We used three-phase inverter to energize coil pairs of BLDC motor and to convert DC to AC current using three pairs of inverter switches. Here we can see a DC voltage source that provides a constant voltages to three-phase inverters, which converts the DC power to three-phase currents to energize different coil pairs at different times. To do that, we have to identify the rotor present angular position, which can be done by getting signals from the Hall effect sensor that will be explained by my other project partners. And this is the output voltage and current when we applied three-phase inverter to the BLDC motor. In our project, we need to control the motor at different speeds. For that, we need to build a PID controller that will adjust the magnitude of the applied voltage. Based on the difference between desired and measured speed, the controller will adjust the duty cycle of buck converter that brings the motor close to the desired value.
Assalamu alaikum everyone. I am Vedran Talagajim, my ID 85. Now we are going to model an Hall effect sensor. Commonly we use Hall effect sensor to time the speed of shafts. In our project, we need Hall effect sensor to determine in which sector our rotor is in. For this, firstly, we are considering the angle of rotation of the rotor, the angle beta. If the angle of rotation is from 0 degree to 60 degree, it will be in sector 1, as you can see from the figure. It will be in sector 2 if the angle of rotation is between 60 to 120 degree. In this manner, we can determine and summarize the angle of rotation and its corresponding sectors as follows. From the previous table, we have noticed for each complex rotation of the rotor, the angle moves from 0 to 360 degree. In each rotation, the angle must return to 0 degree. We have used remainder block for this purpose. Again, we have used another constant term 360 degree so that it gives remainder from division of the angle of rotation by 360 degree. Another gain is added here as the number of poles to the remainder. For implementing the logic, if the angle of rotation is between 0 to 60 degree, it will be in sector 1. We have used this block. Here, we have compared the remainder with the help of relational operators and logical operators. If both conditions are met, the AND gate gives 1 as output and the sector gets 1. Again, if either of the conditions are not met, then AND gets give 0 as output and the rotor is in another sector. In the same manner, we have implemented the remaining logics and thus we can identify the sectors as per angle of rotation. Here, there is a method to notice that at each time, only one of these outputs will be desirable and all of the rest will be 0.
Commutation logic, buck converter, and final output, ID 1706072. Commutation logic, BLDC motors rely on external controllers to achieve commutation. Put simply, commutation is the process of switching the current in the motor phases to generate motion. Mechanism, there are 6 possible ways of energizing the coil. By commutating two phases at a time, the stator magnetic field can be rotated, which will cause the rotor to turn and end up in the positions shown here. The rotor angles are measured with respect to the horizontal axis, and there are 6 different rotor alignment, each 60 degrees apart. This is called the 6-step or trapezoidal commutation. Commutation chart for switching operation in the inverter. Commutation logic is basically like a table containing all of the possible switching pattern. Here, the first 3 switching pattern has been shown in the picture. Here, the sector position is sensed and corresponding logic sequence is outputted so that the right switching pairs are turned on to energize the right coils. This is the commutation block of our project. Buck converter for DC voltage adjustment. A buck converter steps down a voltage from its input to the output based on the controller duty cycle. To control the on-off state of the switches, we have connected them to the PWM signal generator complementarily. The modulated voltage is used to control the motor speed and is fed to the inverter. Final output. Here the motor is successfully following the desired speed as the modulated DC voltage is changing to cause the motor to follow the speed. Now we are in the project module. In the data inspector in real time, we can see that the desired speed is successfully followed by the measured speed. Now we are going to show the hardware implementation of the project.
In this project, we have used motor, 12-volt battery source, Arduino Uno, IR sensor, and LCD display. We have built an IR sensor based tachometer using the PWM pin 5 of the Arduino, connecting it with the Darlington transistor to drive the motor. Now, as we turn on the motor, the RPM of the motor is greater than the preset value. So, the PWM input of the motor is decreasing, making the motor speed decrease. And now, as our project mate increases the preset RPM through the regulator, as the RPM of the motor is below the preset value, so the PWM input of the motor is increasing, making the motor speed increase.